So as I was telling, if you have to use your thiol as one starting material, the other starting material will be chlorobenzene, is it not? And what is the nature of thiol? Is it an electrophile or a nucleophile? Thiol, yes? Yes, yes, nucleophile. It has electrons on itself, right? Lone pair of electrons. Thiol is sulfur atom looks for electron deficient centers, nucleo. This is nucleophilic in nature. What is the nature of the benzene ring? Is it electron rich or electron deficient? Benzene ring.
Electron rich.
So how can you combine two electrons? Yes, how can you combine two electron rich species? You cannot combine two electron rich species. Is it not? Therefore, you cannot use an alkyl thiol and connect it to a equally electron rich aromatic ring. Therefore, therefore think of an alternate synthetic method. Yeah, think of an alternate synthetic method. Yes, think of an alternate synthetic method. What is the other way around now? What is the other possibility? Instead, I will use a aromatic thiol and try to link it with, I will use an aromatic thiol and try to link it with alkyl chain. So alkyl chain can be not audible, not audible. Okay, I'm sorry. If I am not audible, I'm sorry. Okay, 1 second. Yes. Am I audible now? Am I audible now? Huh? Am I audible now?
Yes, sir. Yes, sir.
Yes, yeah, because I got a message that I am not audible. Yes. Yeah. Radha madam, am I audible to you?
Now it's okay, sir. In between, it was not like that.
Yeah.
Now it's correct, sir.
Yeah. In fact,
Thank you.
I have tried a lot to fix my Wi-Fi issues in my home, but you know, because of this lockdown, the technicians won't come so easily now.
That's okay, sir. That's okay. We can.
Yeah, I'm living with this issue basically of very unstable Wi-Fi connection. It's fine. I know things are not ideal always. Therefore, don't try to use a thiol or alkyl thiol. Rather, you use an aryl thiol, and link it with an aliphatic chain. And you can make aliphatic chain nucleophilic or electrophilic depending on the living group you put there. Is it not? So what would be a synthesis? Actually, working synthesis of this would be, you take this aryl thiol and put what here? Living group at this position. Example, halogen, alkyl halide. So I can take an alkyl halide, example of benzyl chloride, and react that with thiophenol. So you get chlorine displaced and sulfur attached here. So why did I give this example? Like in case of an ester, you did not have a single, I mean, there was an option to you. There are two routes of synthesis. But in case of this target molecule, thioether, there is almost no option. You have only one route of synthesis. Okay, so there is no option. You have only one route of synthesis. Therefore, how did we design such synthesis? It is simply based on our knowledge of organic chemistry, particularly the knowledge of reaction mechanisms. Is it not? Now, we have learned a lot of things in organic chemistry, particularly in organic reaction mechanisms, such as this, for example. Now you see this vinyl benzene, and you want to do this addition reaction of this HBr. You have two conditions of addition reactions to double bonds, right? Which are those two famous conditions, Markovnikov's addition and anti-Markovnikov's addition. So you just do an Markovnikov's addition, you get usually a secondary halides, whereas anti-Markovnikov's addition, you get primary halides. So Now, we are now looking into a concept called regioselectivity of a reaction. So we also have the knowledge about regioselectivity. If I alter the condition, I can get altered products. I can change the chemistry of the products by altering the reaction conditions. Instead of just HBr, you add a small amount of peracid. Major product becomes primary halide. Without peracid, your major product is secondary halide. Therefore, the concepts of regioselectivity we know. And we also know that regioselectivity is many a times dependent on the conditions of the reaction. So what is the lesson number 2? What is the first lesson? The choice of your starting materials can be sometimes fixed or can be there can be alternatives. You can choose a lot of different starting materials for the same target product. What is lesson number 2? That it is not just the choice of starting materials. Your reaction condition is also equally important to get your product of choice. Is it not? Fine. Now you see, this is a bromination reaction. Take aniline and brominate. It's a very spontaneous reaction. Reaction which is one such rare reaction in organic chemistry which gives you 100% yield. Usually organic synthesis, the reactions not go to full completion. You don't get 100% yield always. But this is one such rare reaction. You get 100% yield because every time you add a bromine group, that further activates the ring towards electrophilic substitution. Because NH2 is an electron donor, bromine atom is an electron donor. So as you add more and more electron donors, the activation goes to very high levels. So 100% reaction is over for bromination of aniline. Now I tell you, I don't want tribromoaniline. You give me monobromoaniline, parabromoaniline. Example. How do you do this? How do you do this? So controlled bromination you have to do. How do you do this? Yes. It is in CS2.
Changing change the solvent.
The disturbance. Yes, madam. CS2. Carbon disulfide. I mean, as far as possible, I request here. Please try to avoid these background noises. And sometimes it becomes out of our control, but it's better that you keep your phones muted. Only when you want to speak, you can mute your phones. Oh, okay, fine. Using CS2, that could be a method. But what I wanted to show you is the usual method what we follow in our laboratories. What is that? You just mask the amines reactivity. Instead of taking amine, you take acetanilide, acetylated aniline. So your acetanilide is not so much electron donor as compared to free amino group. Therefore, we have this, yes, hiding the group. Correct, madam, Radha, madam, hiding the group. This is called masking the group, hiding the group, or protecting the group. So when you protect this aniline using an acetyl group, instead of getting 3 bromine atoms linked, you get a single bromine atom link. Still the reaction is good. You have some 84% yield, but you wanted an aniline, right? So you remove this acetyl group later and get aniline, parabromoaniline. So in this way, you can modulate the reactivity of the substrates. Is it not? You can increase the reactivity of a substrate or decrease the reactivity of the substrate based on some small changes of the groups. Fine. So now, okay. So now we are fairly equipped. We are having some good set of skills like the knowledge of reaction mechanisms, modulation of reactivity, alteration of reaction conditions. So if you have a combinations of all these things, we are very comfortable. We can easily synthesize such compounds, such small compounds like these compounds. We can easily synthesize them using all the knowledge we have of choosing starting materials, choosing reaction conditions, or a protecting group, or maybe the catalyst is required sometimes, not required sometimes. It's good. So we can go up to small molecules like this comfortably. There's no problem. Fine. You don't require retrosynthesis for this. See, till now I haven't spoken anything of retrosynthesis yet. All that I'm doing is just playing with the knowledge already we have of organic chemistry. Is it not? It's fine. Now, when I show a molecule like this, complication starts. Because a molecule like this is fairly big enough and having a lot of functional groups and a long chain, alkyl chain also. So you start thinking that is there only one way of synthesis of this, or is there many ways of synthesis, multiple ways of synthesis of this? In fact, as the molecule becomes bigger and bigger, the number of ways towards the target molecules increases proportionally. Is it not? Like, for example, if you have to just nitrate benzene or do some acetylation, benzolation reactions, you have only one way. But as the molecule becomes bigger, the number of ways increase proportionally. Is it not? I mean, do you accept or not? As the molecule becomes bigger and bigger, the alternate ways we have is also increased. Do you accept this point? Do you accept this point?
Yes, sir. But yield is matter.
That's okay. Yeah, that's fine. Yield is decreased. Always in a multi-step synthesis, yield is a problem. That is fine. We will address that issue also later. But the complexity of the molecules increases the combinations for the synthesis. See, now, okay, I will tell you one thing, yeah. At this point, I would clarify this. Retrosynthetic analysis is more a design and planning domain rather than execution domain. Hope you understand the meaning of this statement. It's more concerned with design and planning of a synthesis, retrosynthetic analysis. So the terms of yields, byproducts, practical difficulties, separation, isolation, purification, of course, they are very important components of organic synthesis. I'm not ruling that out. But they are not so much influencing our decision for a pathway. It is more design and logic and planning. It's like, for example, you now want to construct a house. What do you do first? Do you simply go to the site and start constructing, dig the mud and start erecting a foundation? Huh? Do you do that? Or rather you go in a very planned approach? In the sense, first you talk to an engineer, get your plans ready, and then consult a contractor, and that Mestri will come. He will also discuss with you. And then after enough discussion and convincing yourself that this plan is constructible, then you are going to build your house. Is it not? So retrosynthesis is more that engineer's work, architect's work. They're planning and designing a building rather than constructing it in actual sense. Fine. Okay. So that's what. But okay. Now let us increase the complexity of molecules. Now I have taken a molecule called epothelone, and this is a natural compound, natural product. You see, it has a lot of functional groups, and it's a macro cycle. Alkyl chains are there. And of course, if I ask you to choose starting materials for this, you come up with your own answers. There are many alternate pathways to make this molecule, not just one. As well as this, you see, and what is this compound? Yeah, this is vitamin B12. And why? a very big complex molecule, vitamin B12, and you look at the stereo centers. How many stereo centers? Almost every alternating carbon is a stereo center. And when there are stereo centers, your synthesis becomes proportionally difficult. Then you have to work at a stereochemical, stereoselective, and stereospecific ways. Fine, anyways. But why did I show these two things? Because these compounds were synthesized even before the discovery or the invention of retrosynthetic analysis. Okay, so please remember, molecules as complex as chlorophyll, vitamin B12, steroids, all these things were synthesized without knowing retrosynthetic analysis at all. I hope you know very well-renowned organic chemist by name Woodward, R.B. Woodward, Robert Brown Woodward, who is from US. He was a master of organic synthesis. He could synthesize a lot of these complex natural products. And in fact, he was awarded Nobel Prize in 1960s. But he did not use retrosynthetic analysis to synthesize such molecules. But what's the problem? As the molecules became diverse, we actually try to look into the thought process, is it not? Why did Robert Woodward choose these starting materials, not that? All these things are the questions always come to our mind, right? But there was no thought process recorded. Why it synthesized in this manner? Why didn't in other manner? All these things. So what happened? You can even, for example, one sec. I'll just share my screen. Yes. One second, just one second. Give me a second. Okay. So you can, somebody can ask, it would have been better for me or better for a practicing organic chemist if Robert Woodward had explained me the design of his synthesis of chlorophyll. If E.J. Corey had explained me the design, or for example, Casey Nicolo, again a world-renowned world-renowned synthetic organic chemist who synthesizes natural products, Casey Nicolo, if he can explain me the thoughts that went in his brain arriving at these starting materials. So what's happening there? Just by instead of simply appreciating their practical synthesis, we will try to appreciate their thought process also. Okay, so that's what led to the origin of this new field of science called retrosynthesis. For example, I've shown you a molecule. It's an alkaloid, tropinone, its name is. Look at the structure of this molecule, a bicycle. So can you ever imagine, by looking at the structure of this molecule, that it can be made using these starting materials like succinaldehyde with dimethylamine and a dicarboxylic acid like this? Can you imagine that it can be made through these three starting materials? Hello? Hello? Can somebody comment on this?
Sir.
Can you imagine, just by looking at the structure of this tropinone, that you somehow your succinaldehyde can be a starting material for this? Can you think? At least in the first chance, at the first look, can you think like that?
No, sir.
No,
Basically, we'll think
not.
of some cyclic.
Definitely not. It is difficult. But look at the synthesis. It's actually done through the simple starting materials like succinaldehyde with dimethylamine, simple starting materials. And you get a intermediate like that, a ketone, which can be decarboxylated to get your tropinone. But if somebody gives you this scheme for the synthesis of tropinone, Are you not tempted to ask him or her, what made you to choose these starting materials? How did you choose these starting materials? Are you not tempted to ask? Yes, like benzene from acetylene. Correct, madam. Okay. So don't you feel like asking? Yes, good. Yeah, madam. Yeah, correct, Radha, madam. Okay, you are referring to one more synthesis. So her point was this. Can anybody imagine that I can make benzene using acetylene's 3 molecules? It's not, definitely. So somehow that happens.
Cyclization.
Yes. Yes.
Cyclization in terms of iron.
Cycloaddition reactions happen. So somebody gives the synthesis. Don't you feel like asking him or her, why did you choose this starting material, or how did you choose? What is the logic behind your design? Hello? Don't you feel like asking them? Hello? Yes, of course we feel. Is it not? So now let us just see how the molecule was envisaged to be made out of these starting materials, simple starting materials. So there is something called a broken line here. The bonds are broken. So this is called a retrosynthetic analysis. Fine. So what is retrosynthetic analysis? So what is the meaning of this word retro in English? What is the meaning of the word retro in English? Hello? Okay, are you listening? Am I audible or what?
Backward.
Yes, sir. Yes, sir.
Yes, yes.
Audible, sir. Backward.
Yeah, what's the meaning of this word retro? Retro music, Rajesh V. Yeah, good. Yeah, retro music. So Rajesh, you are a fairly good lover of music. Rajesh. Rajesh. And come online, yeah, Rajesh. Speak. Okay. It seems he listens to FM radio too much. So there are programs like retro music. Yes, backwards. You are moving backwards. Retro means you are moving backwards. Correct. So in this backward direction of movement is summarized.
Imitating from the past, futures, like that.
Past, going to the past. That is retro. Correct. Yes. So you cannot go to the past actually. The time is lapsed. You can always go back to the memory.
No, we can refer at least to what they did.
Good. Yes, madam.
We
Yes,
can
correct.
refer and we can.
You have memories of the past, right? You have
That
memories of the past. And we can refer to what the things have happened in the past. So basically retro is that. So the word retro means going backwards, basically, as madam was pointing out, going backwards. Now, the same going backward philosophy, principle, we use for design of our synthesis. That becomes retrosynthetic analysis. Going backward from what? From where? From your target molecule. If this is your tropinone is your target molecule, usually before the advent of retrosynthetic analysis, they were going in a forward direction. Take molecules, build them, and get your product. But retrosynthetic analysis is from your target, looking at your target, you should dissect it out into smaller building blocks, which can be potential starting materials. It's not always that if you dissect whatever the fragments you get are starting materials. Dissected out into practically possible starting materials. This is called retrosynthetic analysis. Okay, so it's like now you look at a house and dissect it out into smaller components. The room is here, the hall is here, the kitchen is here, and then you have to join them later into meaningful pieces. That becomes a house. So this is what retrosynthetic analysis is. And as I told you, retrosynthetic analysis is not a synthetic strategy. I mean, it's not a practical synthesis of a molecule. It is only the design of the synthesis. It is planning of the synthesis, the logic of the synthesis. That is what retrosynthesis is. It's almost like algorithms here. Okay, I hope you know of the use of algorithms in your computer science. So algorithms. So if you want to execute something in computer science, through computers, you write an algorithm for it. Using that algorithm, the computer works and execute things as you want. Fine. So similarly, retrosynthesis is an algorithm of organic synthesis. First you write the algorithm and then execute the synthesis. Fine. And as always, an algorithm, for the same execution, a number of algorithms can be written, can be coded, but some would be a complicated algorithm, some can be a simple algorithms. It all depends on the programmer, how he writes the algorithm. Similarly here, it all depends on the chemist, how he designs his synthesis, retrosynthetic analysis. So, in fact, this is a picture which I have taken from E.J. Corey's Nobel Prize lecture. Why is E.J. Corey important to our discussion now? Professor E.J. Corey was the inventor of retrosynthetic analysis. He started conceptualizing, formulating, developing this concept of retrosynthetic analysis. So he shows a diagram picture of a tree, and this is the synthesis arrow mark, and this is the retrosynthesis arrow mark. Fine. So in the synthesis, of course, if you consider this tree as your target molecule, this is your target molecule. So in the synthesis, you take smaller building blocks, build a tree. In retrosynthesis, start from tree and go to its building blocks. Fine. So that is what the purpose of the principle of retrosynthetic analysis is. Just small example, very simple example of retrosynthetic analysis. Now, what is this compound? Phenylalastic acid, is it not? And this phenylalastic acid, if you want to make it phenylalastic acid, you can break the bond here and you get the actuals of retrosynthetic analysis we are going to learn in the next class. What are these double-headed arrow marks, all these things. But as of now, you just understand this much. You can break a bond and then get something called synthons. You can add atoms and groups to the synthons and get starting materials. So how do you plan the synthesis of phenylalastic acid? You take benzyl bromide and sodium cyanide. Cyanide displaces bromine, gets benzyl cyanide. Simply do an hydrolysis. You get COOH. Fine. So phenylalastic acid can be disconnected into these two starting materials, benzyl bromide and sodium cyanide, based on the principles of retrosynthetic analysis. So what are these principles? How to disconnect and break our molecule into simple starting materials. If you learn this thoroughly, this is a very useful skill for your research purpose. Okay, looking at the compound, you will get a fair idea how to synthesize this. What are the starting materials I can use to synthesize this? Or what are the reactions I can make use of to synthesize this compound? Okay, so